So let's try to repeat what we did last time and what we left our subject last time, our discussion. So the question was, what was the space actually required by radio waves and also other kind of waves between the transmitter and the receiver? And what we saw that it made sense to draw ellipsoids between the transmitter and the receiver. To draw ellipsoids, and the ellipsoids now connect points that represents the same difference. So if this was the position of our obstacle here in this plane, this is distance to the transmitter, distance to the receiver. Ellipsoids actually connect points that represent the same difference in length. So this length here denoted R transmitter, R receiver. Now that R transmitter plus R receiver is now D transmitter plus D receiver. This is a straight shortest distance plus some difference. And for our purpose, it made sense to take here an integer n times lambda half. And we called these ellipsoids the Fresnel ellipsoids of the order n, where n is an integer. N is now 1, 2, 3, and so on. And we called, so this was the Fresnel ellipsoid number n, and actually between number n minus 1 and if this was n minus 1 and this is n, these cross sections here, but just the difference between n minus 1 and n minus n was the Fresnel zone. Number n. Only the first Fresnel zone, the n is equal to 1, is equal to a circle. The cross section is a circle, while all the other Fresnel zones are rings. The radii, our approximation for the radii was of the Fresnel zones. So rho n was equal to square root of n times wavelength times dx drx dx plus drx. And this is already not the exact radius, but it's an approximation. It's already an approximation where this rho n has to be still quite smaller than distance to the transmitter and distance to the receiver. Which is true in most practical cases. In most practical cases, angles are very small here, and this rho n here, if I draw it, rho n here, rho n is much smaller than the horizontal distances. In radio links, this is usually the case. So it made sense to divide the space into Fresnel ellipsoids or cross sections into Fresnel zones. Though these things do not provide an immediate answer. You saw if we have an obstacle that is perfectly circular, we had a polished ball, a polished steel ball, polished and hardened steel ball, polished to exactly the same radius from a ball bearing, otherwise the ball bearing wouldn't run. We saw the Arago spot. That was the example, the typical example and not everything is simple with waves. And the Arago spots doesn't happen only for electromagnetic waves, it also happens for other kinds of waves, including longitudinal waves, including sound waves. So all these things we are talking here are totally independent of polarization, because we started with the sum of Huygens sources, and Huygens sources do happen for all kinds of waves. In fact, they were invented, they were thought about by Huygens almost 3 centuries ago. 3 centuries ago, observing waves on the even just two-dimensional waves on the water surface. So what does that mean for us for our typical link with obstacles? The typical link with obstacles is that between the transmitter and the receiver, we have an obstacle, and the simplest form of this obstacle is a knife edge obstacle. So we have here the transmitter, the receiver, and here was the h was the height of the obstacle above the connection, the direct connection between the transmitter and the receiver. And the additional loss, so the electric field in the receiver, if I just draw it here, electric field without the phase, we are just looking at the magnitude, and here we look at the height of the obstacle. The electric field was something like that. The electric field, where this line here was E infinity, this was E infinity half of E infinity. When we the obstacle just touches the direct connection between receiver and transmitter, we lose exactly half of the Huygens sources, we lose half of the field, 1/4 of the power. So above here rho1, and if rho1 is here, minus rho1. Below minus rho1, so if the obstacle doesn't even touch the first Fresnel ellipsoid, here we have almost undisturbed. Undisturbed field in this region here, in this region, undisturbed field. Above here, above rho1, here we have an approximation for the attenuation of this obstacle is minus 16 approximately, minus 16 dB, minus 20 dB times logarithm of base of 10 of height of the obstacle divided by rho1. So rho1, the first Fresnel ellipsoid, is for us really an important measure for the obstacle height. If the obstacle is below minus rho1, we have undisturbed field, almost undisturbed. There is some oscillation, but some small oscillation around E infinity. This peak here is slightly over 1 dB. So let me understand the accuracy. We can do the calculations here. The accuracy with radio wave propagation is very poor. We do not have 6 decimal places here. If we calculate everything to 1 dB accuracy, that's perfect, because we even don't know what is the shape of the obstacle here, what is exactly on top of the obstacle, and that all that may affect propagation. While for here we have the decay of the field, decay, and this decay is quite a complicated function here. We have to calculate over the clothoid, over the solution of the Fresnel integral, while we have an approximation here. Above rho1 we have an approximation, but let's make it clear. that this approximation maybe only holds between rho1, okay, rho1 on one side is smaller than h, or smaller or equal, and perhaps here 5 rho1. Beyond 5 rho1, if you have very high obstacles here, diffraction is very sensitive to what is on top of the obstacle, or what is the exact shape of the obstacle. So 5 rho1, I would put a question mark here, because we don't know exactly what happens. In any case, the attenuation here is very, very high. Now, what we are going to do today is to see what, this first hour, we should see what can we do on top of the obstacle. Is there anything we can do over there? Put a passive repeater. Put some passive structures, because a passive structure does not require a power supply. So what could we do from passive ideas here? We could put here two antennas just interconnected to the other antenna. Yes, but these two antennas have a surface, certain surface, and we cannot do this thing very large, so here we have two radio links in series. That's difficult. What we could also do here, we can put a mirror. That may be more efficient than two antennas. So we had two radio links in series with two antennas. But actually, a mirror with a surface of a mirror may be equally efficient, because mirrors usually have a very good reflectivity. Gamma is equal to -1 for radio waves, not for optics. In optics, you have bad mirrors. And this thing could work. So let's try to do the calculations of a link over a mirror, because antennas are much more difficult to manufacture than the mirror. But if they have a comparable area, their efficiency is comparable. So we have comparable efficiency without the complication of building two antennas and connecting them together. What is the power that actually reaches the mirror? The power that actually on the mirror is now power of the transmitter multiplied by gain of the transmitting antenna. So this is R transmitter, R receiver. Multiplied here and so divided by 4 pi R up to the transmitter squared. So this power is distributed over a sphere, and now multiplied by the surface of the mirror. Does this mirror really contribute? The whole surface contributes? Yes, it contributes, but don't forget the projection. Don't forget the projection here. So we are here at we are coming down at an angle theta. So here I should multiply this surface. The useful surface of the mirror is multiplied by cosine of theta. Don't forget that. If theta is the angle of this ray falling onto the mirror. We don't have right angle incidence. In fact, if this theta goes up to right angle, we almost have no projection, very small projection of the mirror, and then this thing may become inefficient. Then we have the link in the other way, the other link. So the link from the mirror down to the receiver. From the mirror down to the receiver, we get the power we get in the receiver is now power that we have on the mirror. The mirror may have some gain of the mirror, because it behaves like a directional antenna. The mirror is actually an illuminated aperture, and it has some gain, some directivity. It has some directivity times the gain of the receiving antenna times what here? Times lambda over 4 pi r receiver, and all this squared. If I write the Friese equation now for the link from the receiver to the from the mirror to the receiver. And finally, I need this gain of the mirror. What is this? The gain of the mirror here. Gain of the mirror is now 4 pi over lambda squared, because it's a uniformly illuminated aperture, times its surface. Its surface is area of the mirror times the angle cosine theta, because also here I have this the same angle theta for the reflection of the mirror. Now let's try to put all this together, what we have here. Put one equation into another, and also this one put in here. So, what is the power we get in the receiver? Now it's power of the transmitter. Okay, I have gain of the transmitter, gain of the receiver. They both take place a row here. Then I have lambda squared actually cancels out. I have 4 pi squared here, 4 pi here, and 4 pi here. So I have 4 pi squared. 1 over 4 pi squared. Then I have 1 over r to the transmitter squared, 1 over r to the receiver. This is also squared. I take it from here. And I have further this item here, and I have the same item here. Area of the mirror times the cosine of the incidence angle. So I have a mirror squared cosine squared of theta. So this should be now the complete expression, what I have here. The complete expression with one question. Still have one. Does it make sense to have a flat mirror here? Wouldn't it be much better to have a curved mirror to focus the radiation from the transmitter going to the receiver? Or it's better to have a flat mirror? What do you think now? It's better to have a flat mirror, like I made the calculation here, or it's better to have a curved mirror? Well, one issue is to compare the surface of the mirror. We should compare it to the surface of the first Fresnel zone, A1, the surface of the Fresnel zone. Usually what we have, the usual condition is that A mirror times cosine of the angle is way smaller than A1. This is equal to pi rho1 squared, because we know that for a microwave link, you remember last time, for the microwave link, we had rho1 14 meters. 14 squared is 200 meters squared, time pi is 600. So if I take the example from last time, rho1 was 14 meters. In this case, A1 is somewhere around 630 meters squared. This is a pretty large surface. 600 meters squared. This is a square with a side of 25 meters. 25 meters by 25 meters. This is way too large to put on top of a mountain. It's way too expensive. 25 by 25 meters, perfectly flat surface. Further, don't forget the cosine term. The cosine term further decreases this A mirror. So to cover the whole first Fresnel zone, we would need an extremely large mirror. That's not practical. So practical solution is that this is much smaller. If this holds true, then all the summation of all phasors over the surface, all Huygens sources on the mirror, we have an in-phase condition. Of course, when the mirror is perfectly adjusted for the direction of the receiver. This is the practical. And in the practical word for practical mirrors, this is much smaller, and this means flat mirror. We have all the contributions bouncing off this mirror surface in phase, and since these contributions are in phase, a flat mirror will work here. We only need a curved mirror when we need to correct the phase. And we need to correct the phase as we raise to areas that are comparable to the area of the first Fresnel zone. We know that the first Fresnel zone just flips the phase. From the center to the edge of the first Fresnel zone, we just have a phase flip of 180 degrees of pi radius. So because this is much smaller, we need no phase correction here. No phase correction, and flat mirror is a perfectly good solution to have a flat mirror on top. We do not need any curvature because we do not need to correct the phase, as long as it is much smaller than rho1, than A1, the area of the first Fresnel zone. So I should also indicate this first Fresnel zone has an area AN. All Fresnel zones have the same area. They are equal to A1. They are equal to pi rho1 squared. Because all the rings here have the same area as the central circle of the Fresnel zones. So what is AN? What is AN? AN, just to maybe we didn't do this last time, is the area of the circle. So it's area of the ring is the outer ring, rho n squared, minus pi rho n minus 1 squared. And if you work this thing out, if you square to such expression, so you just see that n minus 1 is just equal to 1. So this is just equal to pi rho 1 squared. All Fresnel zones have the same area. And for us, the Fresnel zone, I told you, it is not that the beam has a circular cross-section, because when something is perfectly circular, we have the Arago problem. But this is for dimension purposes. What is the size of our mirror? Our mirror is much smaller, especially its projection is much smaller than the rho 1. Usually the largest mirrors that are used are perhaps 100 square meters here, times the cosine. 100 square meters times the cosine. So 10 meters by 10 meters, they may be even smaller. Such mirrors were used for point-to-point radio links up to perhaps 10 years ago. There are many of these passive repeaters installed in Slovenia, because in Slovenia we have many mountains. And we have many such mirrors installed. You can still see on the mountains. You can climb the mountain and look how the mirror was built. But the links are no longer there. They already, because of the use of optical fiber cables, these microwave links are no longer competitive to optical fiber links. Because of optical fibers, these things are no longer in use. You can no longer see the antennas at the end of the links. So this does no longer exist, and this no longer exists. This was torn down 10 years ago, approximately 10 years ago. But you can still see the mirrors on the mountains, and these mirrors will survive for many years, because it just costs lots of money to tear the mirror down from the mountain. And you can climb the mountain, you can see these mirrors, and you can... the mirrors had an advantage. An advantage that maybe I can draw it here. The advantage of the mirror is what? If I have many obstacles, like this, and I have, say, the transmitter here, and I have the receiver here, Usually the buildings of 2 post offices. And I put the mirror up here, up on the mountain here. So here I have reflection of this mirror. A mirror. Where is the advantage here? The advantage here is that the angle theta goes towards 0. Theta is very small. So cosine theta goes to 1. So have the mirror not in the middle of the link, having the mirror outside, because the cosine theta becomes very small, and we have very efficient use of this mirror. Top of the mountain. One mirror that I see it every day is the mirror for the link from Nova Gorica to Ajdovština. I always drive the highway from Nova Gorica to Ajdovština. And the mirror is actually located on the mountain Nanos, so that's further east from Ajdovština. But you can easily see it because it's very large, this mirror. You can easily see it from the highway. Every day I drive over there, I can see this mirror. So this is a good solution to place mirrors outside of our direct connection between the transmitter and receiver, to have the theta going towards 0, having cosine theta going towards 1, so having a very efficient use of the area of this mirror. And this was actually built in many locations. There are many such mirrors located in quite strange locations, because the location of the mirror is usually not close to the transmitter and receiver. It's not in the middle. We are not placing the middle of this on this small mountain here. We are placing the mirror on a much taller mountain where we have it available. We are placing it on a much taller mountain. In this maybe well outside, this is convenient to have it outside the direct line of sight between the transmitter and the receiver, because we use more efficiently the area here of the mirror. The mirror is not the only thing we can do. Returning to this picture here, we could do something more on this picture. If you remember again the discussion of last time, we had transmitter, we had the receiver, and we had a knife edge type of obstacle here. So a mountain ridge, disturbing at the height h, disturbing our link from the transmitter, from the receiver. Well, we discussed putting 2 antennas here. That's the most expensive solution, making 2 large antennas. With this, these antennas should in fact have the same, for the same link performance, should have the same area as the projection of the mirror. A mirror times cosine theta. But we could also do something else here. We could draw the Fresnel zones here. Now this Fresnel zone is on the mountain, but at a certain distance we get with this Fresnel zone on my mountain top, and we also get over the mountain. So what we could do, if we have access to the top of the mountain ridge, we could shade at least part of our Fresnel zones here. So we could put our 2 poles here to support the structure. We could shade this zone, and we could shade this zone. So we could build a diffractor. In place of the mirror. This was a mirror. And 2 antennas. Again, a diffractor, we want it small. We don't want any large structure here. We don't want any large structure. What we do with the diffractor, if we look at the phasor sum, real and imaginary axis, you remember that the sum was going along a spiral. And this spiral, this phasor summed over the spiral, summed up to E infinity here. If I draw E infinity is here, up to the center E infinity. And just the first Fresnel zone, here first Fresnel zone was twice E infinity. You remember our integral was oscillating, the result of the integral was oscillating, but it was converging very, very slow. We make many circles here. So what we do with the diffractor here, with the diffractor we leave free just a few Fresnel zones. Say this Fresnel zone here, we may not end up with the ridge exactly on the boundary of the Fresnel zones. Say we may end up with the ridge here. And then we leave the first Fresnel zone free, the first available Fresnel zone, it's not the first zone here. So we have this summation. Then we shade the odd Fresnel zone, we left the even free. We have another free, another even free here. Oh no, sorry, not here. Not here, I should go inside the ring. Should go inside the ring. So not here, this was wrong. Erase it. I could go along here, this one here. Here I could make my summation. Going for half a turn is just covering the one phase flip. And then what I have next I have this final summation here. So our summation here for the links goes which way? We don't sum this one, we don't sum this one, we don't sum the ones that are shaded. So the outer shading is done by the obstacle. Then I have shaded this area here. I will draw the shaded area, I will draw it here. The shaded, this one is shaded. So this one from here to here is shaded. And we shade also, this one is shaded, and I also shaded this one. This is also shaded, what I drew it red. This is shaded, and the outer part of the spiral is shaded by the obstacle itself. So I want to explain how I'm doing the summation. So the summation, how is going right now? If I draw here another complex plane, showing just the summation because that's already too cramped. I have one half turn here. Then I have another half turn here. So this was, the first one was this one. Say, let's call this zone A, zone B, zone C. So this is A, this is B is here. And then I have the end of the integration up to here, and this is C. And my whole phasor now is the electric field I get is here. The whole phasor is here. The electric field inside the receiver. Just to explain how this happens. So I can remove here even Fresnel zones, leave just odd Fresnel zones free, and I have summation with such a diffractor. And this diffractor will actually amplify our field here. What comes from the transmitter will be amplified in the direction of the receiver. Will be focused, not amplified, but focused towards the receiver with the diffractor. What is the calculation for the diffractor? The diffractor has a surface of a diffractor. What is the link calculation right now? Everything stays the same as here, only we should consider issues over the diffractor. So the angle theta is now here. The angle theta is now here. So the actual area, useful area of the diffractor is a diffractor times what? Times sine theta. Not cosine theta, but sine theta, because the effective area, so a diffractor, effective, is now multiplied by sine theta, because the diffractor is now at right angle with respect to our mirror. So it's sine theta, so the whole link equation now is P inside the receiver is P of the transmitter times gain of the transmitter, gain of the receiver, 1 over 4 pi squared, 1 over R of the transmitter squared, yes, 1 over R receiver squared. But now I have here A of the diffractor squared sine of theta squared divided by pi squared. Why by pi squared? Because I have this inefficient summation over half circles. So I lose half of the field because I shaded half of the Fresnel zones. And further, I'm not summing this in phase, but I'm summing along a curved line here. And this is just the factor pi we already discussed with the Fresnel lens last time. So now we can make a direct comparison. What is the efficiency of the mirror compared to the efficiency of the diffractor? This factor of pi squared in the denominator, this is minus 10 dB. Of course, the Fresnel lens is 10 dB less efficient than the dielectric lens. This is already a negative point for the diffractor. But the geometry is now much better. If we have this this very flat condition, so that the height of our obstacle is much smaller than the distance between the transmitter and the receiver, then the diffractor has an advantage, because sine of theta is large, cosine of theta is small. So there is an advantage of putting up on the hill the diffractor if the angle theta is close to 90 degrees, close to pi half. And this is typical for small opticals over a long link. This is typical. Yes. But there are issues with the diffractor. This advantage is only valid if we have access to that precise point of the mountain ridge. And that precise point on the mountain ridge usually has an owner, and an owner will make us pay for that lot to build our diffractor. So this spot here may be pretty expensive in the practical world. So I could shift the diffractor along the ridge. But if I shift the diffractor along the ridge, say, if I put the diffractor here, if I build it here, the diffractor, then the shape of this diffractor becomes quite complicated, you see. It's no longer horizontal strips, it's strips at a certain angle if I don't have access. So these things need to be calculated. It needs to be calculated for the position, exact position of the diffractor. It needs to be calculated for the actual wavelength. The diffractor only works for one single wavelength, while the mirror is broadband. The mirror works for any wavelength. While the diffractor does not. So that's a disadvantage of the diffractor. One advantage people do not understand is that the tolerances, the building tolerances of the diffractor are much less stringent than the mirror, or worst of all, the antennas. The antennas have to have a very accurate surface. The mirror also needs an accurate surface, while the diffractor, the position of the diffractor is not that critical. And this is an important point of the diffractor. Unfortunately, diffractors have almost never been used, at least in our country, where they could be installed. They have not been installed, they have not been used, very seldom. I have never seen a diffractor on a mountaintop. But the building tolerances, the construction tolerances of a diffractor are much less stringent than that of a mirror. Just one detail about the mirror. You install your mirror on the mountaintop and then it works? No, it doesn't work. You have to point this mirror very accurately to hit your receiver on the other side. And this pointing of the mirror, considering typical links in our countryside here in Slovenia, you have adjustment screws on the mirror and you have to adjust the nuts of these screws and slowly adjust the mirror trying to hit the receiver. This adjustment in Slovenia usually took 1 week of work for several people. So this work was very expensive. These mirrors were not that expensive to build. They were very expensive to adjust, to hit with the reflected ray, hit exactly the receiver. And this adjustment, moving a structure of 10 meters by 10 meters, weighing several tons of weight here, moving this thing with screws from the calculated position, because first you calculate where does your mirror have to point. But then there are construction tolerances. When you build this thing on a mountaintop, you don't know where did they exactly position the mirror. And then you have to adjust it. And this adjustment is very time consuming. So this was another problem against mirrors. And diffractors was lots of misunderstanding from the people. People maybe understand how a mirror works, but they certainly don't understand how a diffractor works. And when the people at the post office don't understand how something works, then it's a disaster. Like internet. The post office never understands how internet works. So internet and post office, this thing don't go together. And it's the same thing with the mirror. So this is what we can say about mirrors installed on mountaintops. Unfortunately, this is a technology that is no longer being used here. This is part of the past right now. But you can still see, when you climb mountains, you can still see these mirrors, and you are invited to climb up to the peak that actually holds the mirror. This is not usually the tallest mountaintop. It's the one that's most efficient to see both sides and see how the mirrors were done. Okay. I would prefer to do the break right now, a few minutes before the end, because I have 2 other lectures that are much more demanding for the next 2 hours. I will need more time the next 2 hours for the 2 lectures that follow.